Okay, so last time we were talking about solving linear systems of differential equations. Get this open over here. So ones that look like this, and just to kind of walk us through the process of how this goes. Then we set up the matrix of coefficients for the system, calculate the eigenvalues for the system, and then based on the eigenvalues, we have a form for a guess for the general solution for x, or maybe y if you want to do it that way. And we're going to use the same general solutions that we used with second order differential equations, namely if we get distinct real roots, then we have the sum of exponentials. We get one repeated real root, and we put this t in front of the second term. And if we have complex eigenvalues, then we've got the exponents and the trig functions. And then once we have the eigenvalues and a general solution for one of our equations, we plug this into one of the differential equations and solve for the other. So the way that we did it last time is we found a general solution for x, we plugged it into the equation for x prime and solved for y. You could very well use your eigenvalues to write a solution for y and then plug this solution into y prime and solve for x. Either way you want to do it is fine. And so I want to start doing with some of the examples that we didn't get to last time on worksheet 17. And then move on into worksheet 18. But before we get started, any questions? I just want to point out one thing. I posted a couple of announcements this morning, and I just want to make sure everybody saw them. So one thing is I set up what I'm calling a study hall for the class, for lack of a better word. It's just a Zoom room where you can go. You should be able, I'm hosting it, but I set it up so that you can jump in without me being there. You should be able to share screen. So that's just a place for those that have been on campus. The math department has really nice spaces where students can work on things. And so I want to try and just kind of recreate that space virtually. So if you're like, hey, do you want to meet at 2 and work on differential equations? Here's a room for you to go if you want to do that. As well as the link for office hours. I was talking to some students, and I just wanted to double check this. Are students able to host their own Zoom rooms? Do you guys have permissions to do that? You do. Okay. Yeah. Okay. So I think some students are having trouble doing that. So if you are, you can come here. You can always set up your own rooms as well. Okay. And then the other thing, you should have gotten some announcements about this policy, but they're doing a similar type of modified pass-fail policy for this semester. And the modification is they usually don't have a P+ option. So you could change to a pass-fail, and then if you get a C- or above, you would get a P+. That can count towards any requirement, any CLAS requirement at least. It'll count towards math major. You can use it as a prereq to enroll in another course. So really there's no difference from getting a P+ versus a letter grade, except the P+ doesn't factor into your GPA. It doesn't have any ramifications on credits or financial aid or anything like that. If you get a P, that would be like equivalent to a D. And in that case, you would earn credit for the class. It's not going to affect your GPA, but you can't use that as a requirement towards a CLAS requirement or a major requirement or a minor requirement. And then the change this semester, last semester, there were NPs, not passes, meaning if you got below a D, you didn't earn credit for the class, but it didn't affect your GPA. And I just want to make sure that now you're aware, if you go to this policy and you don't pass the class, you get below a D-, that would affect your GPA. And kind of the other thing is there's a deadline to do this by the 25th of October, which is this Sunday. So I think you've got some information to go on as far as how you're doing in this class at this point. And so if you do have any questions about whether this makes sense for you or not, that's probably a private discussion that we could have. And so, yeah, there was a question about, does this affect scholarships, financial aid? I don't believe so, but this is a CLAS policy, so I would say you should check in with your CLAS advisor just to double check that. So just so it's clear, since I am like the advisor for the math department, I'm not going to be the one that processes any of this. I don't need to approve any of this. Nobody needs to approve it. There's what's called a schedule adjust form. You fill it out. The action that you would take is, I want to change to a pass fail. It looks like the instructor needs to sign the page and the dean's office needs to sign the page, but for this, we don't. Just the student needs to sign it, and I don't need to approve it. I don't even know if I'll see who decided to change. I don't think I'll even know, but you're welcome to tell me if you want to. Any questions about that? Okay, so just keep in mind there is a deadline for that for the 25th. Okay, so let's take a look at some of these problems that we didn't get to last time. And I want to give you guys a chance to practice this some more before we move on into the next worksheet. And so these problems at the end of this worksheet are pretty much what you're going to be what you might have started working on for the homework that's due next week. Okay, so just to kind of refresh ourselves, we did work on this one at the end of class and did discuss it to some extent. But were there any questions about this one? Okay, and so when you're doing your work on the homework, just be sure that you're providing the steps. So I'll just kind of walk through B together as if I were handing in this homework assignment, and then I'll give you a chance to work on the next couple ones. So yeah, so in B, we've got this system, x prime is x minus y prime is 2x minus y. So step one, and this part, the stuff in green, I'll just say you don't need to write. You don't need to like indicate all of the steps that you're doing, but we would set up this matrix 1, minus 1, 2, minus 1. Okay, so I'd like to see that. We'd like to know what matrix you're using, and then we'd like to see the characteristic equation as well. And so from this, kind of the next step would be, let's find and solve the characteristic equation. So remember, to do that, we take the determinant of this matrix where we subtract these lambdas from the diagonal entries and we set it equal to 0. Hazel has left. She's given up on this class already. Okay, and then the resulting equation should be some quadratic equation. If we're working with 2x2 matrices, if you happen to have a 3x3 case, then you'll get a cubic equation. Yep, then we take the determinant of this matrix, we simplify, and I'll just say you don't need to like write out all of the details of the algebra at that stage, though if you don't, you might make a mistake. So it certainly doesn't hurt or take too much time. Let's see, and then this would give us no lambda term, and then we would have minus 1, and then we have plus 2. If I'm looking at this correctly. So this gives me lambda squared plus 1 is equal to 0. Any questions so far? So then this gives us eigenvalues of plus or minus I, for example. So we have complex eigenvalues here. And so from this, kind of the next step is, okay, great. Now we've got a solution for either x or y. I'll say x. So this tells me that x is going to equal c1 times the cosine of t plus c2 times the sine of t. Okay, our alpha value is 0 and our beta value is 1. Any questions? Okay, then we want to go ahead and solve for y. And so we can calculate x prime by taking the derivative of our previous answer. Oops. So that's our x prime, and then we set that equal to x minus y. We're going to use this equation, and we're going to plug in these values, these equations here and here. Oops. And then the only remaining unknown in that would be y. So I'm going to set this equal to x, which was c1 cosine t plus c2 sine of t minus y. So this is our x prime is equal to x minus y, and then we solve for y. And I'm going to write this with my sine and cosine terms grouped together. And so again, what we saw last time was that these coefficients in the equation for y should depend on the arbitrary constants that we used in the equation for x. And it could be some combination of those like we see here. That's what happens when you have complex roots. Okay, and then my final answer should be solutions for both of those, right? We should have a solution for x and the solution for y, and we should have only two general constants in that solution. Okay, any questions about that process? Okay, so let's give you a chance to practice, since certainly different story, trying to do these on your own. So I want to give you a chance to make sure you're comfortable with that. And let's see which ones might be good to think about. Yeah, so let's do, well, let's do these two, or at least start with C, try and do D, see how long that takes. And I'll just leave the last two. If you get to them now, great. Otherwise, I'll just leave them as additional practice. But I think if we do a couple of these, you should start to pick up on the pattern. Any questions before break us up?
Was there a reason why you started with X and not Y?
Nope. X comes before Y in the alphabet, that's all. The equation for X was on top, but otherwise there's no reason. Yeah. Okay, breakout rooms are open. Good luck, help each other out. Try not to just all work independently, but check in with each other. And let me know if you have any questions. All right, I think everybody is back. Great. Okay, so let's kind of touch base on how these went. I was able to check in, I think, just about everybody with the first one at least. Um, sorry, this is taking a second to connect. Here we go. Okay, so in 3, right, we've got matrix over here, which then gave us characteristic equation, which had 1 repeated real root of 9. So you could write this as x first and get this solution, and then plug that into this equation up top. So this would be x prime is 12x minus 3y. And then the goal is to solve for y. So I can bring the y over here, bring all these other terms to the other side. And we've got 3y is equal to 3c1 e to the 9t minus c2 e to the 9t plus 3c2t e to the 9t. And then we could just divide by 3. And that would give us c1 e to the 9t minus c2 over 3 e to the 9t plus c2t e to the 9t, right? So we divide each of those by 3. And so
I had a question.
yeah.
So wait, how did those 9s get in front of the first part of the x prime?
Because we would take the derivative of e to the c1 e to the 9t, which gives us 9 c1 e to the 9t, using the chain rule on that.
That's where I screwed up for my answer. I forgot to drop down the 9.
Yeah, so you've got to use a chain rule on this, and you've got to use a product rule on that. Yeah. Yeah, and so let me just say that you very well could write this out. More commonly, we would combine these terms. And write it out like that. But either way you want to leave it, that's fine. Our solution should be a set of equations for x and y. Did anybody do this process solving for y first and then finding x? Since I just want to see these two solutions side by side, since there were some questions about, does it matter which way we do it? No groups did it that way?
We did.
Um,
My group did.
okay, and so what did you get, Brian, when you, y would look like that, and then what did you get for x?
It's the same thing, only a plus C2 over 3. So yeah, see the minus there?
So you got C1 plus C2 over 3 e to the 9p.
Yeah, I think that was the only difference.
Okay, let me just check that later just to make sure that these are the same. But in the end, what we're saying is that you could write it either way, and just be aware they might seem seemingly different if you're working with somebody else, but they should be equivalent. So all this is really saying is that the coefficient in front of the t e to the 9t is the same in both equations, and we see that behavior over here as well. Yeah. And so there should be some consistency as well with how we write the coefficients in front of the term that doesn't have the t in it. Okay, and any questions about that? Okay, and then checking in part D seemed like groups were able to get solution eigenvalues, which were 3 plus or minus 2i. So we have complex roots, and that would give us a solution here for x of t. And then we could take this and substitute it back into the equation. I'm just going to write up the solution here in case you got that far, but I'll put out the steps when I post this online so you can check it in more detail. But for this one, what I got was a minus C1 plus 2C2 over 5. And just to kind of get a feel for what these solutions might look like, they look a little bit more complex when you've got complex roots. And I'll just say that this very well is probably an example where it might make sense to first give the solution for y and then solve for x, just because it's easier to work with this equation to solve for x probably than it might be to solve for this one when we solve for y. So you can see that's why we're getting these fifths over here. Okay, are there any other questions?
For you grading and stuff, do you want us to leave it as like a numerator as an expression, or should we break up it into fractions, or do you not care at all? I know it's the same answer. It's kind of just a matter of preference.
Yeah, I don't care. And I told the grader when she gets to this not to care. So if you do wind up seeing something like that, just let me know. But I don't care whether things are simplified or reduced or whatever. This was focused on the differential equations part of it. I'm not as concerned on the simplifying stuff. Yeah.
And in terms of tying this all together, what we just found would be the growth for these if it was like population growth.
Yeah, so what we found were, if these were two populations, then this is telling me how is population X changing with time. And it's going to be like a little cyclical thing. And then we can talk about, and this is telling us how population Y is changing with time. Yeah. And then the phase plane equation that we were working with last week would tell us how X and Y are related to each other. So there are different ways that we can explain the dynamics here. Okay, any other questions about this before we take a look at the next worksheet? I will put up solutions to these as well if you want to get some practice, extra practice. This is very, very similar to what a lot of your homework assignment is on. Okay, so next, let's take a look at worksheet 18. Which deals with the stability of equilibrium for these systems and how we can kind of use our solutions to get an idea of what the phase plane would look like. So we've talked about how to do it with null clines and these sorts of things. So I want to talk about how we can use the eigenvalues and eigenvectors of this system in order to come up with a sketch for the phase plane. So we worked with this one last time, and we were able to find a solution to that system down here. And so what I want to think about now is what happens if we have certain initial conditions. And ultimately, what I'm going to want to do is sketch a graph of all of this down here in part 3. And we're going to graph this in the phase plane. So we're going to look at X versus Y. And so let's first think about if we were to start right here at 3, 0, which is what question 1 is asking us. And so we haven't considered initial conditions yet. And so given some initial conditions like this, we could plug these into the differential, into our general solutions and solve for C1 and C2, for example. And so plugging this in for x, for example, we could set x equal to 3. And when I plug in 0, I would get C1 plus C2, right? And then I can plug this in for y, and we're saying at time 0, y is equal to 0. So we don't need to kind of change how we use initial conditions to solve for these arbitrary constants. So this tells me that C2 is 0, and thus C1 is 3. So our solution to the initial value problem would look like this. And so this is just saying, right, if initially we don't have anything in population Y, then we're never going to have anything in population Y. And then we can write out what this solution would look like in the corresponding phase plane, just thinking about it in terms of x and 0 and y. And what this is telling me is if I start with an initial condition on the x-axis, then that solution is going to always stay on the x-axis because, right, the y-coordinate is always going to be 0.
Should that be e to the 3t?
Yeah, thank you. I think I changed it at some point. It should be, that's the one for C1, yeah, or thanks. So that means if I start at this point on the x-axis, I'm not going to go off the x-axis. I'm going to stay on this axis. And in particular, as t increases, which way am I going to head? To the right or to the left? So as t increases, what's going to happen to the value of x?
It's going to increase.
Going to
Y
increase.
is always 0. It has to stay on the x-axis the whole time.
Yeah, so we're going to stay on the x-axis, and then the question is, are we going to move to the left or to the right on the axis? Because we do want to indicate the direction of time here, and as t increases, the value of x is going to increase, so we're going to be moving to the right. And so just like we did with null lines, over here we can see that if I start on the x-axis, we're going to stay on the x-axis and head out to the right. And if I happen to start with a negative x value, then we can do a similar analysis, which says now we're going to head, it's going to get more negative as time goes on, so we're going to move to the left on that side. Any questions about those observations? Oh, sorry, there's something in the chat. Ah, okay. And then we could do a similar sort of thing with this initial condition at 2, 1, so 2 minus 1. So that would be 1, 2 minus 1. So let's say that's starting at this point over here. And checking these conditions, we've got that y0, that should be -1. And when I evaluate that at 0, that tells me the value of C2. That's not right, excuse me. When I plug in 0 into this differential equation or this solution, we would get -1/2 C2. So this tells me that C2 should be equal to 2. So don't forget, we have this little constant in front of the C2, which we need to take into account there. And so then that tells me for x, when we plug in times 0, if we get 2, this would give me C1 plus C2. And since C2 is equal to 2, this tells me that C1, that doesn't look right, is equal to 0. And so our solution here is C2 e to the minus T2, and y is equal to minus, what am I doing? Sorry, so we're gonna take these values for C1 and C2, right, and plug them into these equations. So C1 is 0, that term goes away. C2 is 2, so for x, we get 2 e to the minus 2t. And when I plug these values in for y, plugging in C2 equals 2 in here, right, we get minus e to the minus 2t. And this is not quite okay to say. I can't quite factor out something from a pair of coordinates. But what I'm trying to say is that if we start at a point to -1, then we're going to stay on the line through that point. It's always going to be the case that the value for x is going to be -2 times the value for y. So for this one, I'm just going to choose to write this in terms of how does y depend on x, because that's normally how we graph things in the plane. That's not even close to that line. So here's this line, y is equal to -1/2 x. And so this means if I start on this line, we're going to stay on that line. And in this case, as t goes to infinity, this is going to get really, really small, right, because of the negative exponent. And this is going to get really, really small. And so again, what we'd want to know is, are we moving out away from the origin, or are we moving in towards the origin? And because of these negative values, we can see that as t goes on, these values are going to approach 0, both of them. So that gives me these directions over here.
Yeah.
These are like null lines in the sense that these vectors along these lines are going to have the same slope always. It's just not that they're horizontal or vertical, but they might be slanted. But at least we can see if we start on any point on this line, I know where I'm going to stay on that line and either move in towards the origin or move out away from the origin. Was there a question?
Yeah, I had a quick question.
Sure.
Can we backtrack real quick? How did you
Mhm.
get y equals -1/2 x? I think I'm just not following that section.
Yeah, so we've got y is equal to minus this, and x is equal to this. So all we're saying is if I take y and multiply it by -1/2, I'm going to get the, sorry, I should get this as, I need to multiply y by -2. Sorry, that's right. So it should be a -2x.
Okay. So
Yeah, but all we're saying is by comparing these two values, for any value of t, we're always going to get that x is -2 times the value for y. All right, since I could write it like that. No, I'm sorry. I had it right. We could either write it as x is equal to -2y, or similarly, you could write it like that. So I just chose to write it that way because that's normally how we graph lines, y equals mx plus b.
gotcha. Okay. Thank you.
Yep. And this is going to tell us exactly how all of the other solutions are going to behave, since we can't cross over one of these lines. So this tells me once I can identify these very special directions, that allows me to fill in the rest of the solutions in the phase plane. And so we've got this equilibrium at 0, 0. And here we can see that in this case, this happens to be a saddle, or what we call semi-stable. Since some directions go in and some directions are coming out. Any questions? So the question that I might have now is like, I gave you these directions, but how would we find out these special directions? And that relates back to eigenvalues and the so-called eigenvectors associated to them. So number 4, we kind of sketched that general picture up here. So any questions before we take a look at eigenvectors more generally?
Honestly, I'm still a little confused how you got your diagonal line there.
So we plugged in the initial condition that when x is 0, when t is 0, x is 2, when when t is 0, y is -1. So that's where this was. That's what allowed us to solve for C1 and C2. So just let me, so that part's okay. And that gave us these solutions over here. And so if I write this as coordinates, that gives me x is going to equal 2e to the -t, y is going to equal -e to the -2t. And if you are not liking this, then you can rest assured that this is going to be a line through the origin. And one way that you can think about it is if I take y over x, that's going to give me -1/2. So I can write this as that. There's another way to kind of get there. So all we're saying here is that the ratio of y over x is constant, and that's why we're sitting on this line through through the origin.
Yep, that cleared it up perfectly. Thank you.
Yep. Anything else? Okay, so so here's what we mean by an eigenvector. So first kind of thing just to mention here, and we did this on the previous worksheet, is that if you go through this system and find the eigenvalues for this system, you're going to get that there are two eigenvalues, 3 and -2. And then what we want to do is find these kind of special directions. And these vectors, v1 and v2, we are going to call these things eigenvectors. And here's kind of what the definition for an eigenvector associated to a certain eigenvalue is. So let me just kind of illustrate how we can identify these two special directions, since we probably are not going to come up with them off the top of our head. So in this case, we've got this matrix A.
Is there a reason why we changed the polarity from the statement to the bullet point?
You mean here?
Correct.
Here? No. Sorry. Yeah. And so either way, right, these 2 points sit on the same line. So
Okay.
kind of thinking about whether we're over here versus like over here. Yeah. That was just an honest mistake. Sorry. So we've got our matrix over here. And let's just write it like this. So what it means, again, to be an eigenvector is we have these two eigenvalues. So that's where the 3 came from here. So this vector, I'm going to call it xy over here, just because v1 and v2 are individual eigenvectors. So what I want to do is find this vector xy so that when we multiply that vector by the matrix, it's equivalent to just multiplying that vector by 3. So to solve for this, we have a system of two linear equations that we would get. So on the left side, we would have 3x plus 10y. And over here, we would get 0x minus 2y. So that's that part of it when we do that matrix multiplication. And then on the right side, we have 3x and we have a 3y. And then we solve this system. And what you're going to find is that we're not going to get unique solutions here. You should find that we're going to have an infinite number of solutions. So let me just say that if you find that there's only one unique solution here, that's a good indication that you either found the wrong eigenvalue or you just made an error in trying to find the eigenvector. So yeah, so from this one, we could solve for y, and what we can see over here is we would get 0 is equal to 5y. So this equation implies that y has to equal 0. And then we can take this condition and plug it into the top equation, and that would tell me 3x is equal to 3x. And that's great, again, because we should find that there are lots of solutions here. So this means x is anything. So this tells me this eigenvector xy looks like X can be anything and Y can be 0. For example, 1, 0 would be an eigenvector. 2, 0 would be an eigenvector. So all we need to do is just give one possible eigenvector. We just need to know the direction. So all of these eigenvectors should have the same direction. So I'm going to call this the eigenvector associated to the eigenvalue of 3. And then we could do something similar for the other eigenvalue, but let me just kind of pause here for a second. Any questions?
So you're just representing that like kind of as a unit vector then? Because
I did. It doesn't need to be a unit vector.
Oh.
So there's nothing special about that. I could have picked a 2 here and a 0 here.
Could you just leave it as X? Like it could be arbitrary?
We're going to want to pick a specific value for when we start to write out, when we use these to write out general solutions. So I think it's nice to just pick your favorite value for X or Y and just give one concrete vector that gives me the direction. Since we have enough unknowns floating around, we're going to have a C1 and a C2 and a C3 and a C4. We can just pick a value for X so that we don't have to deal with so many arbitrary constants.
Okay.
Okay, and then we could do something similar with the other eigenvalue. And in this case, that was -2. And so this would give us 3x plus 10y is equal to -2x. And then in the second equation, we've got -2y is equal to -2y. So we can see from that equation, that's going to be true no matter what value we pick for y. And plugging that into this equation, basically, this equation really doesn't tell me anything, right? This is going to be true no matter what we pick for x and y. So it's really this equation which is going to give us the relationship between x and y. So leaving y arbitrary, in the top equation, we would get something like 10y is equal to -5x. So this tells me that y is -1/2 x. So this means any vector that has of this form would be an eigenvector, just plugging that relation in the place for y. So again, what's nice is just to pick your favorite value for x. I'm not very excited. My favorite number is 1. So I'm going to plug 1 in there, and that gives me eigenvector here. And notice that this has the same direction as this kind of special vector that we used the initial conditions for in the previous problem. Any questions? And just to connect this back before we end things for the day. So we found this system way back over here. And in the course of solving this, we got lambda 1 was 3, lambda 2 was -2, one eigenvector was 1, 0, another eigenvector for this one was 1 minus 1/2. And this just gives me an alternate way of writing out the general solution. In what's called vector form. So in this case, this would look like this up. So we could write this out in vector form like that. I'll get right back down to that in a second, sorry. Okay, that was not very helpful. I just want to compare this to the solution that we found earlier. And if we kind of match this up, you can see they're equivalent. This solution has no e to the 3t term. That's because we had a 0 over here. And this coefficient of -1/2, that is not totally unrelated to how we found these eigenvectors. So I'll just say the textbook does it entirely this way. They don't say find x, then plug it in and find y. They find eigenvectors. I'll just say that when you're dealing with the complex roots, this becomes a total mess. So I don't recommend using eigenvectors when you have complex or repeated roots. Sorry, we're out of time. So really the only thing that you're going to need to use eigenvectors for are to get a picture for the phase plane like that. So you've got one homework assignment problem, which is kind of similar to question number 5. So feel free to get started on that. We'll pick up with this in class on Monday, and that should help you with that remaining homework problem if you haven't gotten to it yet. Okay, so sorry for keeping you a couple minutes over time, but have a nice weekend, everybody. And if you've got any questions about this material, I've got office hours tomorrow, 10:30 to 11:30. Otherwise, feel free to use the room to work with your classmates. Okay, have a nice afternoon, everyone.
Thank you, you too.